Hello and welcome to today's lesson on binomial expansion of polynomials of the form a plus b raised to the power n. We'll review the use of the Pascal Triangle to find the coefficients of the binomial expansion. We'll also introduce some new concepts, the factorial and combination, and compare it with the use of the Pascal Triangle to find the coefficients of the binomial expansion. We'll also find the nth term of the binomial expansion and work some examples. We'll start with the factorial. It is denoted by this symbol. On your calculators, you'll find the factorial symbol on your calculator. And the factorial of 0 is 1. 1 factorial is also 1. The factorial of 2 is defined as 2 times 1. And the factorial of 3 is defined as 3 times 2 times 1. And this gives us 6. The factorial of 4 is defined as 4 times 3 times 2 times 1. This also evaluates to 24. The factorial of 5 is also defined as 5 times 4 times 3 times 2 times 1. So this is how we define the factorial. So 5 times 4 is 20, 20 times 3 is 60, and 60 times 2 is 120. So we say the factorial of 5 is 120. Factorial of 6 is also defined as 6 times the factorial of 5. If we look at the procedure, how we found the factorial of 5, the factorial of 4, we found the factorial of 5 by multiplying 5 times 4 times 3 times 2 and times 1. So if we want the factorial of 6, it is 6 times 5 times 4 times, so we shorten it and write the factorial of 6 is 6 times the factorial of 5, and that gives us 720. 7 factorial will also give us 7 times 6 factorial. When we compute, this will also give us 5040. So that is the factorial. In general, if we continue this to the number n and we say we want n factorial, then n factorial is going to be defined as n times n minus 1 times n minus 2. And this will continue till we get times 1. In the nutshell, what we are saying is that if n equals, say, 8, 8 factorial is equal to 8 times 8 minus 1 times 8 minus 2 times 8 minus 3. This goes on till we get to 8 minus 7, which is 1. And so here we're going to get 8 times 7 times 6 times 5 times 4 times 3 factorial. So that is what we're going to get. 8 factorial will be 40320. So you can go ahead and compute the factorial for 9 and 11 factorial, or any number that you deem fit, you can. So that is the concept of the factorial. Before we proceed deep into the binomial expansion, the other term apart from the factorial I want to introduce is what we call the combination. If I have n items and I want to choose r items out of the n items, I write n combination r. This is also equal to writing NR. So if you have seen this anywhere, they mean the same thing. By definition, it is defined as n factorial over n minus r all factorial times r factorial. Therefore, as an example, if I have 5 items and I want to choose 2, what it means is that I have 5 factorial over 5 minus 2 all factorial times 2 factorial possible ways of choosing 2 out of 5 without any order. Therefore, this gives 5 factorial over 5 minus 2 is 3 factorial times 2 factorial. This gives us 5 times 4 times 3 times 2 times 1 per our definition of factorial, and then we are substituting into our formula up here. So we have 3 factorial is 3 times 2 times 1 times 2 times 1. 2 crosses 2 here, 3 crosses 3, 2 here 1, 2 here 2. And 1 also cancels that. So in a nutshell, we have this to be equal to 10. The next example is if we have 6 combination 3. This is equal to 6 factorial over 6 minus 3 factorial 3 factorial. We can write this as 6 factorial over 3 factorial times 3 factorial. And this will be given by 6 times 5 times 4 times 3 factorial. Because I see 3 factorial in the denominator, I write 3 factorial times 3 times 2 times 1. The expansion of the last term here is from this 3 factorial. So we can cross out 3 factorial and 3 factorial. 3 times 2 is 6. So this crosses that, and we have this to be equal to 5 times 4, which is 20. Okay, so that is the definition of combination. Now, in our last lesson, we learned how to expand polynomials of the form x plus 3y raised to the power 4. And we said that the coefficients of this expansion was given by the Pascal triangle. Now, we defined the Pascal triangle as follows. We have 1 and 1, and we said that the ends are always 1. 1 plus 1 is 2, and we repeat 1. 1 plus 2 is 3. 2 plus 1 is 3, and 1. 1 plus 3 is 4. 3 plus 3 is 6, and 1. So, if we want to expand x plus 3y raised to the power 4, we have to use this rule of the Pascal triangle to get the coefficients of the expansion. This is what we studied in our last video lesson. So we're going to apply that, and we have x raised to the power 4, 3y raised to the power 0 plus the second term in this, which is 4 times x raised to the power 3. Note that this is descending, and this raised to the power 1 plus the next term is 6 x raised to the power 2, 3y raised to the power 2 plus, let's come there, 4 x raised to the power 1, 3y raised to the power 3 plus x. Here we have 1, x raised to the power 0, and 3y raised to the power 4. If we want to evaluate this, then this term here, we have x raised to the power 4 plus 4 x raised to the power 3 times 3y plus 6 x squared times 9y squared plus, we look at the terms here, we have 4x times 3 raised to the power 3 is 27, y 3 plus 3 raised to the power 4 is 81, y 4. We can simplify x4 plus 4 times 3 is 12, x3y plus 9 times 6 from this term, we come to this term, 9 times 6 is 54, x squared y squared plus 4 times 27 is 108, x y 3 plus 81 y 4. So the expansion of the polynomial x plus 3y raised to the power 4 is given by the sum of these terms. When the power of the polynomial becomes large, it is difficult to use the Pascal triangle to get the coefficients of the terms in the expansion. So we want to find an alternative to the Pascal triangle. Let's introduce the Pascal triangle again. And we have 1, 1. 1 plus 1 is 2. We have 1. 1 plus 2 is 3. 2 plus 1 is also 3. And we have 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And we have 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And we have 1. We have 1. We have 6, 15, 20, 15, 6, 1. We have 1. We have 7. We have 21. We have 35. We have 35. We have 21, 7, and 1. Okay, so let's end here. But fortunately for us, we see that this is the same as writing 0 combination 0. And here we have 1 combination 0 and 1 combination 1. Here we have 2 combination 0, 2, combination 1, 2, combination 2, 3, combination 0, 3, combination 1, 3, combination 2, 3, combination 3. Okay, so we continue the filling of the table, and we have this as we see. So let's take any and compute to verify if indeed we'll get the values as given by the Pascal triangle. We have the Pascal triangle in white, Pascal triangle values. We know that n combination r is equal to n factorial over n minus r, all factorial r factorial. Let's take any of the values, and I think I hear somebody say we should take 7 combination 2. So 7 combination 2 will be 7 factorial over 7 minus 2 factorial 2 factorial. Okay, so we have 7 factorial over 7 from here. 7 minus 2 is 5 factorial times 2 factorial. Therefore, we have 7 times 6 times 5 factorial all over 5 factorial times 2 factorial. And this we can cross 5 factorial out with 5. We have 2 factorial, so 2 cancels this. We have 3. So this one gives us 7 times 3 is 21. Let's check 21, the value 21 here, with 7 combination 2. And we see that this is 7 combination 2 and the value is 21. Okay, let's take another example. Example 2, we say 6 combination 4. This is equal to 6 factorial over 6 minus 4, all factorial 4 factorial. And this evaluates to 6 factorial over 2 factorial. 6 minus 4 is 2 factorial times 4 factorial. So we have 6 times 5 times 4 factorial over 2 times 1 times 4 factorial. This also crosses with that. 2 here, 1, and 2 here, we have 3. So we're going to get 3 times 5, which is 15. Now let's check what we have. This is 15, and this is 6, choose 4. 6 combination 4. Where do we find 6 combination 4? We find 6 combination 4 here, and that is also 15 as confirmed. Okay, I hear somebody say we should take the last one. The last one is 3. So we have 4 combination 4. Let's see what that one also gives us. 4 factorial over 4 minus 4, all factorial times 4 factorial. This one gives us 4 factorial over 0 factorial times 4 factorial. And as usual, we have 4 cancelling 4 factorial. The answer is 1, because we have 0 factorial is 1. And what do we have? We have here 1, and for combination 4 is also 1. Now that we have seen that both the Pascal triangle and the combination approach gives us the coefficients of the binomial expansions, let us take some examples and use both the Pascal triangle and the combination approach to see if we'll get the same results. It is important to note that when the power of the polynomial is very high, say you have x plus, say 3y raised to the power 25 to compute, it is very difficult to write out all the values for the Pascal triangle before you are able to compute the coefficients of the expansion. So it is very convenient to use the combination approach. So let's go ahead and try to solve some problems using both the Pascal triangle and the combination approach. The first example we'll solve is 1 plus x raised to the power 3. And we are going to use 3 approaches to solve this. The first method, 1, what we'll do is we have 1 plus x to the 3, and we'll use the traditional approach. That's when we multiply 1 plus x, 1 plus x times 1 plus x. We can use the FOIL to multiply these two terms, and then later on multiply it by the last item. So if we multiply these two terms, we have 1 times 1, 1 times x, and that gives us 1 plus x. The second thing is to multiply x times 1 and x times x. So this one also gives us plus x squared. So that in bracket, we can still write our last term here, 1 plus x, because we have not dealt with it. When we sum the terms in this bracket, we are going to get 1 plus 2x plus x squared. That is going to be multiplied by 1 plus x. Using the same approach, we are going to get 1 plus x plus 2x plus 2x squared plus x squared plus x cubed. Summing and grouping like terms, we have 1. These two terms, we can add them together and get plus 3x. We can also add these two terms here together to give us plus 3x squared, and the last term is plus x cubed. If we have something, a polynomial that is raised to the power, say 15, it will be difficult to use this approach. The second approach that we are going to use is method 2, and that is the Pascal triangle. We saw that the coefficients for the third row in the Pascal triangle was 1, 3, 3, 1. You can pause the video and then check. Okay, so first we're going to get 1 plus x cubed will give us, using the Pascal triangle, these are the coefficients. So we have 1, and we have 1 raised to the power 3 times x raised to the power 0 plus 3 times 1 raised to the power 2 times x raised to the power 1 plus 3 times 1 raised to the power 1 times x raised to the power 2 plus 1 times 1 raised to the power 0 x raised to the power 3. So this gives us 1 here. The next thing we are going to consider is this term plus 3 times 1 times x, which is going to give us 3x. The next term is this 3 times 1 times x squared will give us plus 3x squared. And the last term gives us plus x cubed. So we see that both answers are the same. The third method, which is method 3, is to have 1 plus x raised to the power 3. And this, using the combination approach, this will be given by 3 combination 0 times 1 raised to the power 3 x raised to the power 0 plus 3 combination 1 times x1 raised to the power 1 raised to the power 2 times x raised to the power 1 plus 3 combination 2 times 1 raised to the power 1 times x raised to the power 2 plus 3 combination 3 times x1 raised to the power 0 times x raised to the power 3. So when we evaluate this, we're going to get 3 combination 0. Let's leave that. And here we'll get times 1 plus we have 3 combination 1 times, we have here times x plus 3 combination 2 times x squared plus 3 combination 3 times, we have here x cubed. We have 3 factorial over 3 minus 0 is 3 dot 0 factorial plus 3 factorial over 3 minus 1 is 2. So we have 2 factorial dot 1 factorial x. This term gives us plus 3 factorial over 3 minus 2 is 1 factorial dot 2 factorial x squared plus 3 factorial over 3 minus 3 is 0 factorial dot 3 factorial all times x cubed. Now, this then gives us 1 because this cancels that and we have 1 plus here we're going to get 3x plus this term gives us 3x and the last term here gives us plus x cubed. So looking at these three terms 1, 2 and 3, we see that they are all the same. So in our subsequent approach we are going to use the combination instead of the Pascal triangle or going by. At this point, I'll solve a problem to demonstrate the use of the Pascal triangle and combination approach to expand a binomial. So let me take this example, 2x plus 4y raised to the power 5. And I'll first use the Pascal triangle. So this is the problem I'm going to solve. Now, we recall that using the Pascal triangle, the fifth rule was given by these numbers here, 1, 5, 10, 10, 5, and 1. These were the numbers that gives us the coefficients when we want to use the Pascal triangle to expand the binomial. So we are going to use these coefficients, pick them one after the other, and substitute them into the expansion as we go along. So first of all, we write our question. We have 2x plus 4y raised to the power 5. We take the first coefficient, and that is 1. We multiply it by 2x raised to the highest exponent or highest power 5, multiplied by 4y raised to the power 0. Always we are sure that when we add these two exponents, it should be equal to 5. Plus, the next item is 5. That is from here. We multiply it by 2x raised to the power, this time is 4, times 4y, and that will be raised to the power 1. Plus, we take the next coefficient, which is here, 10 times 2x, and this time is raised to the power 3. We multiply it by 4y raised to the power 2. Plus, the next coefficient is 10 times 2x raised to the power 2, multiplied by 4y raised to the power 3, plus the next coefficient is 5. So we take 5 times 2x raised to the power 1 multiplied by 4y raised to the power 4. And we take the last coefficient plus 1 times 2x, and this time raised to the power 0 multiplied by 4y, and that is raised to the power 5. So as we can see, when we add all the exponents, for instance, if we take this and that, 1 and 4, add and we get 5. Now we can simplify. We have 2x raised to the power 5, and that gives us 32x 5. 4y raised to the power 0 is 1. So we move on to the next item, and that is 5 times 2 raised to the power 4 times x raised to the power 4. Or we have 2x raised to the power 4, and that gives us 16x to the power 4 times 4y. We take the next item, this plus 10 is multiplied by 2x raised to the power 3, and that gives us 8x3 multiplied by 4y raised to the power 2 is 16y squared. The next term is this term here, plus we have 10 times 4x squared. 4y raised to the power 3 is 64y3. We take the next term, and that is given here, plus 5 times 2x, and 4y raised to the power 4 is 256y4, plus the last term, which gives us 1 times 2x raised to the power 0 is 1, and 4y raised to the power 5 is 1024y5. Let's make progress. Now we can take this term here, that is 32x5, plus we have the next term here, 5 times 16 times 4 would give us 320x4y, plus the next item is this term here, and that gives us 10 times 8 times 16. 10 times 8 is 80 times 16 is 1280x3y2, plus the next item is this term here. We have 10 times 4 times 64, and that gives us 2560x squared y3, plus the next term is this term here. That gives us 5 times 2 is 10 times 256 is 2560x y raised to the power 4, plus the last item, which is this term here, and that gives us 1024y5. So in a nutshell, when we expand the binomial 2x plus 4y raised to the power 5, this is what we get with its accompanying coefficients. So the next thing we are going to do is to use the combination approach to solve the same problem. 1. We'll look at the second method. 2x plus 4y raised to the power 5. And here we are going to use the combination approach. So the first thing we'll do is 5 combination 0 times 2x raised to the power 5 multiplied by 4y raised to the power 0, plus 5 combination 1 multiplied by 2x raised to the power 4 times 4y raised to the power 1, plus we have here 5 combination 2 times 2x raised to the power 3 multiplied by 4y raised to the power 2 plus 5 combination 3. This is multiplied by 2x raised to the power 2 times 4y raised to the power 3 plus 5 combination 4 times 2x raised to the power 1 multiplied by 4y raised to the power 4 plus 5 combination 5. This is multiplied by 2x raised to the power 0 multiplied by 4y raised to the power 5. We can now evaluate this. 5 combination 0 is 5 factorial over 5 minus 0 is 5 factorial times 0 factorial. This is multiplied by 2 raised to the power 5 is 32 x5 times 4y raised to the power 0 is 1 plus we have 5 factorial over 5 minus 1 is 4 factorial times 1 factorial, and this is multiplied by 2 raised to the power 4 is 16 x4 times 4y plus 5 combination 2 is 5 factorial over 5 minus 2 is 3 factorial times 2 factorial. This is multiplied by 2 raised to the power 3 is 8 x3 times 4 squared is 16 y squared plus we take this term here 5 factorial over 5 minus 3 is 2 factorial times 3 factorial, and this is multiplied by 2 squared is 4 x squared multiplied by 4 raised to the power 3 is 64 y 3. We come down here, we have plus, and the next term is this term here. We have 5 factorial over 5 minus 4 is 1 factorial times 4 factorial. This is multiplied by 2x times 4 raised to the power 4 gives us 256 y4 plus the last term here, and that gives us 5 combination 5 is 5 factorial over 5 minus 5, that is 0 factorial times 5 factorial times 2 raised to the power 0 is 1 times 4 raised to the power 5 is 1024 y raised to the power 5. When we take this term here, 5 factorial crosses 5 factorial, so we get this one 32 x5 times 4 factorial, so this will cross 4 factorial, so we get 5 times 16 x4 times 4y plus the next term is this term here. We get 10 5 factorial over 3 factorial times 2 factorial gives us 10 times 8x3 multiplied by 16y squared plus the next term to evaluate is this term here, 10 times 4x squared times 64 y3 plus the next term is this term here, that gives us 5 times 2x times 2, 5, 6, y 4 plus the last term is this term here, and that gives us 10, 24, y 5. Let's make some room. We can now write the final solution as 32 x 5 from this term here. The next term is that one here, and that gives us 5 times 16 times 4 gives us plus 320 x4 y plus this term here gives us 10 times 8 times 16, and that evaluates to 1280 x3 y2 plus the next term is this term here. This gives us 10 times 4 times 64, and that gives us 2560 x squared y3 plus this term here gives us 5 times 2 times 560. That also gives us 2560x y4 plus the last term, which is the term here, that gives us 1024 y5. So that is the expansion of 2x plus 4y raised to the power 5. And we have the binomial coefficients being the same in both expansions. Now we notice that in the expansion of the binomial, say a plus b to the power n, we use the combination approach, which is given by n combination 0 a n minus 0 b 0 plus n combination 1 a n minus 1 b 1 plus n combination 2 a n minus 2 b 2 plus n combination 3 a n minus 3 b 3 plus this goes on till we get to n combination n a n minus n, which is 0 b n. We can write this expression here in a compact form. Using the summation notation, we write summation r starting from 0 to n combination r, a n minus r, b raised to the power r, where a and b are in the set of real numbers, n is in the set of natural numbers, and r start from 0, 1, 2, 3 up to n. This formula for expanding the binomial is referred to as the binomial theorem. It's used to expand polynomials of the form a plus b raised to the power n. So we take note of this formula, which we refer to as the binomial theorem, and we are going to use this in most of our expansions of binomials. Let us take an example and use it to illustrate the use of the formula. A plus b raised to the power n, we now know it's equal to summation r from 0 to n combination r, a, n minus r, b, r. This is what we have now. So as an example, x plus 2y raised to the power 3, if we compare this example or this polynomial to the formula a plus b, then it implies a equals x, b equals 2y, n equals 3, and r will run from 0, 1, 2 to 3. Okay, so let's try to expand this. We have x plus 2y raised to the power 3. This will be given by summation r from 0 to 3 n. In this case, and our n is going to be 3, but let's put n as it is in the formula, and a is x. We have n minus r, b is 2y, and we have r. Therefore, 3 combination 0, when r is equal to 0, when r equals 0, we have x, 3 minus 0 is 3, and 2y raised to the power 0, plus, because it's a summation, 3 combination 1 for r equals 1, x will be raised to the power 3 minus 1, which is 2, 2y raised to the power 1, plus, when r equals 2, we have 3 combination 2, x, 3 minus 2 is 1, b is 2y raised to the power 2, plus the last term, which will be 3 combination 3, x, 3 minus 3 is 0, and we have 2y raised to the power 3. So on evaluating, we have 3 factorial over 3 minus 0 is 3 factorial times 0 factorial times x raised to the power 3. 2y raised to the power 0 is 1, plus this term here, 3 factorial over 3 minus 1 factorial is 2 factorial times 1 factorial. Then we multiply it by 2x squared y, plus, we move on to this term, we have 3 factorial over 3 minus 2 is 1 factorial times 2 factorial. We are multiplying it by x. 2 squared is 4. We have y squared. Plus 3 factorial, and 3 minus 3 is 0 factorial times 3 factorial. X to the power 0 is 1, and 2 raised to the power 3 is 8 multiplied by y cubed. On summarizing, x raised to the power 3 plus 3 times 2 is 6. We have 6 x squared y plus 12 xy squared plus the last term here 8y cubed. So this is expansion of the polynomial x plus 2y raised to the power 3. We have the binomial coefficients. We have 8, we have 12, 6, and 1. Okay, now the next thing I would like to talk about is how to find the nth term of a binomial expansion. Many a times you are asked to find, say, what is the 4th term in the binomial expansion? What is the 7th term in a binomial expansion? Or find the coefficient of x squared term in an expansion. How do we find that? We now know that if we have a plus b to the n r 0, where a, n minus r, and b r. Okay, the first term, if we denote terms by t, then the first term, which is t1, will be given by n c 0, and that will be a n minus 0 b 0. So in a nutshell, we're going to get n c 0 a n. Okay, the next term, which is the second term, don't forget I'm using t to indicate terms. So we have n combination 1, a, n minus 1, b 1. The third term, t3, will be equal to n combination 2, a, n minus 2, b 2. Let me make space. The fourth term, t4, will be given by n combination 3, a, n minus 3, b 3. So if you look at these terms here, for the first term, the second term, the third term, and the fourth term, you see a pattern that is repeating. If you compare this number, 4 minus 1 will give us 3. If you look at this term here and this term here, you also see that for the third term, there's a difference of 1. When you look at the second term, you see that there's a difference of 1. So we can write the 7th term just by looking at this and say that the 7th term is n combination 6, a, n minus 6, b 6. So in general, we can say that generally the r plus 1 term will be given by n combination r, a, n minus r, b, r. This formula here will give us the r plus 1 term. Every time this is the r plus 1 term, r plus 1 term in a binomial expansion. To find the 4th term, it implies that r plus 1 is equal to 4, and therefore r is equal to 3. Therefore, r is equal to the term minus 1. So if we say the 4th term, it means that r is equal to 3. If we say the 8th term, then r equals to 8 minus 1, which is 7. So that is how we are going to compute the terms in a binomial expansion. Take note of this formula. That's an example. We already solved this problem. So let's find the 4th term. 2x plus 4y raised to the power 5. What is the 4th term in this expansion? So this is a problem that we have, and our solution, 2x plus 4y, it implies that we have a equals 2x, b equals 4y, n equals 5, r is the fourth term. So term r is given by term minus 1, which implies that r equals 4 minus 1, and that is equal to 3. We are to find the fourth term. T4 is n combination 3, a, n minus 3, b, 3. And that, doing the substitution, we have 5 combination 3, a is 2x, so we have 2x, 5 minus 3 is 2, and b is 4y raised to the power 3. So that is what we have. Now we can compute this. Let's make some room. 5 factorial over 5 minus 3 is 2 factorial times 3 factorial. And 2 squared is 4. X squared 4 raised to the power 3 is 64. Y 3. Okay, so on evaluating, we get 5 times 4 times 3 factorial over 2 factorial times 3 factorial. 4 times 4 x squared times 64 y cubed. This crosses that, and 2 here, 1, 2 here is 2. We have 10 times 4 times 64, and this one gives us 2560 x squared y 3. We can check this to see in our previous example if really the fourth term is given by this value that we have here. Another interesting question is find the coefficient of the x squared term in 3x squared plus 1 on x all raised to the power 7. Now, looking at this, we see that a will be equal to 3x squared, b will be equal to 1 on x, n will be equal to 7. In this case, we don't know what the value of r is, but we know that between 0 and 7, the terms tr plus 1 term is given by n combination r, a n minus r, b r. That is the r plus 1 term is given by this. So to find r, n combination r, what is a? Our a is 3x squared, 7 minus r, 1 over x r. We are going to apply some laws of exponents to solve this problem. 7 combination r, and from our laws of exponents, we can split this term here, 3x squared, 7 minus r. We can split it in this form. We can say that 7 minus r and x squared is also 7 minus r. We can split it this way from the laws of exponents. This can be multiplied by x minus 1 r. Now we have 7 combination r, 7 minus r x, using this method x, n, m is given by x, m and n. We can multiply the exponents here, 2, and this term we can multiply them to get 14 minus 2r. This will give us minus r. Now, we are told from the question that the exponent equals 2. So we can write 7r 3, 7 minus r. And once we can see that this term here and the other term here have the same base, we can use the laws of exponents to add the exponents, this term here and that term there, to get 14 minus 3r. Now, once we are told that, let's make some room here. Once we are told that we should find the x squared term, then it means that in this expansion, there will be an x squared term. So we equate the exponents of x to 2 to find the value of r. So here we have 14 minus 3r will be equal to 2. Solving, 14 minus 2 will be equal to 3r, which indicates that 4 is equal to r. So once r is equal to 4, we can substitute it back into our equation here to get the coefficient of the x squared term. Okay, so on substituting, we have t r plus 1 equals 7 combination 4, 3, 7 minus 4 is 3. We have x, 14 minus 3r, which is 3 times 4 is 12. This gives us 7 combination 4, and 3 raised to the power 3 is 27. X raised to the power 2. 14 minus 12 is 2. So on evaluating, we get 7 times 6 times 5 times 4 factorial over 7 minus 4 is 3 factorial times 4 factorial. All this times 27 x squared. We can cross 4 and 4 there. This is 6 and that is also 6. So we have 35 times 27 x squared. And that gives us 945 x squared. The coefficient of x squared in the expansion of 3x squared plus 1 over x, all raised to the power 7, is given by this term here. The coefficient is 945. This is why the combination approach is faster when you are using it to find the coefficients of the terms in the binomial expansion. In our next video, we are going to solve some problems of the binomial expansion and then also give the opportunity for you to also share your answer some questions. You can pause the video and try your hands on this question. X minus 2 on x raised to the power 5. Pause the video and try your hands on it. The second question will be 2x plus 3y. The third question would be 2x plus y. And this one, the answer is 8x 3 plus 12x squared y plus 6xy squared plus y 3. Share your comments and thoughts below in the comment section. See you in our next lesson.